All right, everyone. Hello. I hope you were doing well. I just wanted to go through this optimization problems PDF with you and go through some of the examples together to give you a better idea on how to go through them. These are basically applications for finding global extrema, so absolute max or absolute mins. So for this first example, we want to find two non-negative numbers, x and y, for which this equation here is satisfied. 2x plus y is equal to 30, where if I took my x and took the product of that with y squared, that number would be maximized. So whatever x and y I find that satisfies this, because there could be more than one answer, I want to pick the x and y that satisfy this, and when multiplied like this, give me the biggest number. So here what we'll do is we're going to define the xy squared to be some value, and I'm just going to call it f for now. Okay, which is the thing that we want to maximize. But we have a bit of a problem. Okay, we have function of two variables, x and y. We don't know how to differentiate multivariable functions. We only know how to differentiate one function. So we need to find a relationship between x and y so I can isolate for one of them in terms of the other and then sub it in. But we have been given a relationship between these two quantities. We know that 2x plus y is equal to 30. So using this expression, what I can do is I can isolate, I'll say for my y. You can actually isolate for whatever one you want. Now, keep in mind that our question tells us that we need two non-negative numbers. Okay, so I need to have a note here for myself saying that, okay, remember that this y, this needs to be positive. And because I've expressed my y as 30 minus 2x is greater or equal to 0, that means that if I isolate for my x, so bring the 2x to the other side, it means that my x is going to have to be less than or equal to 15. So you can write it like that. I personally prefer to write the inequalities that are like that the other way. So x is less than or equal to 15. But it also needs to be greater or equal to 0. So that kind of tells me the type of interval that I'm working with here. So now that I have an expression for x and y, what I'm going to do is I'm going to sub my expression for y in here. So x is equal to 30 minus 2x squared. I'm going to expand it. So 30 times 30 is 900. And then minus 60 minus 60, so that's minus 120x. And then I have plus 4x squared. And if I completely expand it to get a polynomial, I'll get 900x minus 120x squared plus 4x cubed. And remembering the x's I'm considering are going to be between 1 and 15. Okay, general, they have to be positive. Has to be less than 15, though, in order for y to also be positive. Okay, so now that we have a function that we want to maximize, we can find our critical numbers. So how do we do that? We find our derivative with respect to x. Okay, so by power rule, I'll have 900, and then I'll have minus 120 times 2, which is 240x, and then 4 times 3 is 12, and then I'll have an x squared left over. I set my derivative equal to 0, and what I'm going to do is I'm going to factor out a 12, and I'll write it with the highest degree first. So x squared minus 20 times 12 will give me 240, so 20x. And then 75 times 12 will give me 900, so plus 75. And now if I go 15 times 5, that will give me 75, and if they're both negative, that works with this plus, and then that will be negative, so all works out well. So 12 times x minus 5, x minus 15. So in other words, our derivative, we get horizontal tangent lines if x minus 5 is equal to 0, or x minus 15 is equal to 0. So the critical numbers that we have are 5 and 15. Now, since we need, again, that x is greater than 0, and we also need y is equal to 0, we have the endpoints. Now, by endpoints, what do I mean by that? Well, we have a specific interval where this will end up working, and that's the stuff that we found in green here. So when you have an interval like this where your value is between 2 points, remember those are called endpoints. So what we're going to do is we're going to check to see what our f is equal to if I plug in these values of x, but also if I plug in my endpoints. And it just so happens that one of the endpoints is the same as one of the critical numbers. Okay, so what do I have to check? So I'm going to have to check, well, one of my endpoints was 0, one of my critical numbers was 5, and the other critical number and the other critical endpoint was 15. So what I'm going to do is I'm going to plug those into my y expression, because remember, I'm looking for an x and a y. And I know that my y is written as 30 minus 2x. So if x is equal to 0, I'm going to get 30. Now, what does my xy squared equal in that situation? So if I go 0 times 30 squared, that value here is just going to be 0. For the case when x is equal to 5, what y does that correspond to? Well, that corresponds to 30 minus 2 times 5, so that would be 20. And if I multiply 5 and then 20 times 20, that's going to give me 2,000. So this number is bigger than this number. So far, this set of points is winning. And finally, if I have 15 for my x, it would give me a y of 0. So when I multiply this x and y together, I would actually also get 0. So what does that mean? It means that the xy squared is maximized if I choose my x to be 5 and my y to be 20. Okay, now let's do more of a physical problem. So say we have a pharmaceutical company, they want to manufacture cylindrical pill bottles with a certain volume of 1 liter, which remember corresponds to 1,000 centimeters cubed. Now, what should the radius and height of the bottles be that'll minimize the amount of plastic is used, so then you can minimize your cost? Okay, so for this type of problem, we aren't really given variables. We have to define them. So because I'm talking about a radius and a height of a bottle, I'm just going to say, let my r be the radius of the bottle. And I'm going to let h be the height of my bottle. And then minimizing the amount of the plastic corresponds to what? It corresponds to, I want the smallest amount of plastic, which is surface area. So it corresponds to minimizing the surface area of the bottles. Okay, which we're just going to call A. So now if I think about, let me draw a little, pill bottle here. Plastic pill bottle. Okay, in terms of my labeling, I have my radius here, and I have my height. Now, with respect to the surface area, what do we have here? So I'm going to have the top and the bottom of this pill bottle. Let's just say the cap and the bottom. It'll be an easy mechanism. Lids realistically are actually a little bit more complicated, but that's fine. We'll assume that they're the same for this problem. So we're going to have the top of the pill bottom and the bottle of the pill bottom, and then the side of the pill bottom. Okay, so we have the top and bottom, which are circles. Okay, and we know what the area of a circle is. The area of a circle is equal to pi r squared. And the sides of the pill bottle, now if you look at a cylinder and if you were to cut it and unravel it, right? So say we cut along here and we unravel it. So we would still have the height corresponding to this, but we would end up getting a rectangle where, where the circumference of the circle of the top, that would correspond to the length of that rectangle. And remember, when we're talking about circumference, that is going to be 2 pi r. Okay, so let me flip back for a second. Okay, so we have the two circles, we need their area, and the side of the pill bottle, if you cut it, it's a rectangle. So the side of the pill bottle is a rectangle. Okay, so for that area, we know that the area of a rectangle, well, that's just equal to length times width. Okay, now the length we said was the 2 pi r, okay, corresponding to the circumference, and the width in our case corresponds to the actual height of the pill bottle. So the surface area of the entire thing, we're going to have two circles, so I have pi r squared, but I have two of them, and then I have the side of the pill bottle, where that area is going to be 2 pi r, which corresponds to the circumference, and then I have my h. But we need a function of one variable. Okay, so I have to somehow now relate my r and my h together so I can get rid of one of them. So either find an expression for r in terms of h and then plug it in, or vice versa. Now, what other information are we given here? We are told what the volume is. And we know what the volume of the cylinder is. The volume of the cylinder is just pi r squared h. So I need to have one function, and we are told that the volume is, now I'm not going to write it in liters, I'm going to write it in centimeters just because the length and the height and all these things are in centimeters. So the volume is 1,000 centimeters cubed. So we can use the volume expression to relate r and h. Okay, so my volume, as I said, let me move this up a bit. This is going to be equal to pi r squared h. And in particular, I'm told that my volume is going to be 1,000 pi r squared h. And now you can isolate for whatever one you want. I'm personally going to isolate for my h because I don't want to take square roots. Okay, so I'm going to write this as 1,000 divided by pi r squared. And note that, you know, your r can't be equal to 0 here, because otherwise h would not be defined. All right, so now let's rewrite our area expression in terms of only r. So 2 pi r squared stays the same, times 2 pi r, but now my h, this is going to be 1,000 divided by pi r squared. So in terms of simplifying, my pi on the bottom and top will cancel. One of my factors of r will cancel since r can't be 0. So I am getting what? I'm getting 2 pi r squared plus 2 times 1,000. That's going to be 2,000. And on the bottom, I now only have that it's divided by r. Okay? Where r is greater than 0. So now I have a function that I can actually minimize. I need to find my critical numbers to do so. So if I take the area of this, okay, so I have 4 pi r. I'm only looking at the rate of change of r. So I'll bring down the 2, so 4 pi r. And then remember, 2,000 over r, we can think about this as 2,000 r to the power of -1. So by power rule, we're going to bring down that -1. So we're going to get -2,000. And then I would get r to the -2, which is the same as r squared. Okay, so I need to now set this equal to 0. And now I need to solve for my expression for r. So what I'm going to do is I'm going to bring this over to the other side. Okay, let me zoom in a little bit here. So I'm going to say 2,000 divided by r squared is equal to 4 pi r. I'm going to cross multiply, and I'm also going to get rid of a factor of 4. So 2,000 divided by 4, that's going to be 500. And then the 4 is gone, and then I have pi r cubed. And I'm trying to isolate for my r, so I'm going to write this as 500 divided by pi. And to isolate for my r, I'm going to have to take the cubed root. So take everything to the power of 1 over 3. Okay, so I get an expression that is absolutely beautiful. 500 divided by pi to the power of 1 over 3. Okay, roughly, what is this equal to? Roughly, if you plug it into a calculator, you'll get 5.419. Okay, so that's our r. And that will tell us what the best height would also be, or what the height corresponds to when we find this critical number. I just have to plug it back into there. And what we are going to do is we are going to do the approximation just because it's nicer to write down. If I want you to make it exact, I will tell you. Okay, but otherwise this is fine. If you plug this into a calculator, you get approximately 10.84. So it's actually roughly twice. The height is roughly twice that of the radius. So in terms of, where can r be defined if there's endpoints, the only restriction is that the radius couldn't be equal to 0. So the radius can't be 0, and there's one critical number. So this automatically is the only thing that will minimize the plastic. So we would have r is approximately equal to 5.419 centimeters. And then that corresponds to a height of approximately 10.84 centimeters. And to confirm this is a minimum, so you could look at the derivative before and after the critical number to check. That's one way to do it. But we know that our a in particular, where is it here? It does represent a type of parabola. When we sub in the r, we have a parabola and we have a plus 1 over r. So visually, we know that roughly this is going to be facing upward. Okay, there may be some slightly odd things. R can't be equal to 0, so as it's close to 0, this term will be a little bit influential. But ultimately, as r gets really, really big, this term is not going to be very relevant. This will be the most important term. Okay, if you think about r in the long term as it keeps getting bigger. So if you were to plot this, this would be the most influential, which is an up-facing parabola. Okay, so cognitively, you're like, okay, upward-facing parabola, that corresponds to a minimum, so that's fine. To be rigorous, we should check to make sure that that area does represent an actual absolute min and not an absolute max. Okay, but this is how you go about solving the actual problem. I hope that was helpful. Thank you.